Okay, next one now. Use the identity to show that log x is an increasing function on x. Okay, so log x equals 1 over x. I'm pretty sure, and I'm sure someone has opened the ticket already, that's supposed to say t and not x. So that would equal, you would have log x would be less than the right Riemann sum, 1 over t delta t. It's the right Riemann sum. Is it called a Riemann sum? And then the left one. Oh no, I can't say that because I'm trying to show that it's decreasing. Okay, so I could say it's the log x is equal to the limit as delta t goes to 0. But 1 over t (1 to x), yeah, but 1 over t is positive. So this will, yeah, so actually maybe the best way to say it is like this. Limit x, log x is the limit as delta x goes to 0. The sum from n equals, maybe I'll change that to n goes to infinity, and from 0 to n, 1 over t delta t, and that is less than the limit as n goes to infinity, sum and 0 to this, I suppose it'd be the upper limit would be x minus 1 over, this is a bit messy. I'm trying to show that because of the it's always positive, it has to be. How about x is less than y? So the integration of 1 over x, 1 to x, 1 over x dt, that would mean it's less than the integration of 1 to y, 1 over t dt, because 1 over t is positive and never equal to 0. Because these are both sums. I guess another way you could also say it is 1 to y, 1 over t dt, that's equal to 1 to x, 1 over t dt, plus x to y, 1 over t dt. And these are all, everything's positive here. So this would be more than just 1 to x, 1 over t dt. So this shows that it's increasing because this is equal to log x, and this is equal to log y. And this is increasing. This shows that log y is more than log x, where y is more than x, and the y has to be more than x so you can do this split. So I think that proof perhaps is a little bit better than what I was trying to do a moment ago. Okay, so we say log y is equal to that, which is a positive, and 1 to y can be written as 1 to x and x to y, and then we can drop this because it's a positive and say it's more than this, which is equal to log x. So I think that's a little bit better. Um, again, we don't really want to include 0, do we? I think we kind of want to have it open here, right? Because x can't equal 0. It's not defined at 0. Okay, and use the previous actually show that the range of log x is minus infinity to infinity. Interesting. How to show that now? Ooh. Interesting. As I used the previous exercise. Maybe this? Because you can say that if x is in 0 infinity, then 1 over x is in 0 infinity. And then log 1 over x equals minus log x. So as long as it's not 0, that means that there's both positive and negative, but it doesn't show that there's every value. And I realized that this proof only works as well if y is more than 1. So now I don't like it so much. I need to try something different. Okay. All right. The derivative of log x, that will be the derivative of 1 to x 1 over t dt. That would be the derivative of whatever the antiderivative function is, 1 to x. So that will be the derivative, of fx minus f1. So that would be the derivative of fx. So that would be 1 over x. Now, for x in 0 infinity, the derivative of log x would be positive, which means increasing. Okay, so I'm more satisfied now. And use the previous exercise to show that the range of log x is minus infinity to infinity. That one I need to think. Okay, I have a pretty ugly proof. So, let's say x equals e power n. And I think we can use the fact that log e equals 1 because log e would be the integration from 1 to e, 1 over t dt. And I'm sure that was, we can take that as a fact because that's like a definition nearly of the e. So x equals e power n, then log x equals log e power n, and then using the product rule we just established, so that's log e times e times e, etc., which would be log e plus log e, etc., which would be 1 plus 1 plus 1, etc., which would be n. And likewise, 1 over x equals e power n. Sorry, we've shown that log 1 over x equals minus log x, so that would equal minus n, where n is any integer. So therefore, the integers are a subset of the range, but the intermediate value theorem implies that the values in between also are part of the range. So if all the integers are part of the range, and the values in between the integers are part of the range, then it must be the case that, well, all the real numbers are part of the range. So i.e. the range equals minus infinity to infinity. Yeah, without any further assumption, conclude that log x has an inverse function defined on that. Well, that's just the conclusion from establishing what the range is, and it's increasing. So if it's increasing, that implies it's injective, and the range is all the real numbers. So if you put them together, then it has an inverse. Whew.